Morning.
Hey, good morning.
Good morning.
Calc 3. Deeper into the cross product we go. All right. Let's grab a piece of paper. Rip 13.4, the cross. The cross product, which we ultimately said yesterday was that if you have U crossed with V, that is equal to the magnitude of U times the magnitude of V times the sine of the angle between those two. So that's a definition of this. So I'd like to deepen your understanding a little bit, and then also, I guess maybe just to note, it's kind of cool that the dot product was so similar. In other words, it was U dot V equal to, well, exactly the same statement, right? Except for it was the cosine of theta. So that's kind of fascinating. And so yesterday we said that really what a cross product can be more, I don't know, simply understood or more easily made sense of as being a torque finder. It's kind of a torque finding equation. And a dot product is like an angle finding equation. That's kind of the best way to look at it. Because this comes up in your assignment, the other thing I guess I'd kind of like to point out is this. Another way this is conceived of, or at least kind of, I don't know, I feel like this is a little bit, I'm not even sure this is helpful. This kind of bothers me a little bit, but the idea is basically this. If you have this vector V sitting over here and you have a vector U coming off at an angle like this, and this is the angle in between, given the fact that taking the vector U and multiplying it by the sine of theta really gives you this length right here. Notice it's a length. So really that represents that height. And basically what we said yesterday is if we took this point right here and it was sort of this far away, and we took this force over here, this is another way I could draw it. That's also vector U multiplied by the sine of theta, because remember it can kind of go anywhere. Then if this is the force and this is the distance, I'll call this point A, then really the cross product could be thought of as the torque. Around that point A. So the V vector is the distance, is how long the wrench is, so to speak, and then the u vector is the force. And we said yesterday, the only part of that that counts is the part that's perpendicular. And so u modified by the sine of theta is going to be smaller. And that's kind of the gist of what we said yesterday. But another way to conceptualize this, if you're just going to multiply those together, then the cross product is in the same exact picture, the area of a trapezoid. Now, I think the cross product is the good one because people actually use the cross product. They use torque to actually find the desire for things to rotate. I mean, this is such an important part of engineering. In other words, if I had a building like this, and I've showed you problems kind of like this, if somebody said, hey, let's make an awning, and this is a cable, and here's this kind of modern porch roof and so forth, you can appreciate that this thing wants to, well, rotate off the wall. In other words, maybe it's attached to the wall right here, but that thing basically wants to rotate. It wants to torque. And so you have to, as an engineer, figure out how much desire that thing has to rotate. How badly does that want to rotate down? Because it's your job to come back and design this cable up here and the connection to the wall and to the heavy roof itself in such a way that that doesn't come off the wall. And so torque is actually an application. So that's kind of cool. But I would at least like you to understand that you can conceptualize this as the area of a trapezoid. Here's how. Let me just erase a little bit more of this since we don't need all of it. Does it make sense to you that since u sine of theta would effectively be the height of the trapezoid? I mean, if I redrew vector v up here and I redrew vector u over there, doesn't that create a trapezoid if I just copy those, make copies of those two vectors? So this is also vector u, this is also vector v. So if you're going to take the length of vector v and then multiply it by u times the sine of theta, which is really the height, isn't that the formula for the area of a trapezoid? So you can conceptualize, since the area of this picture is really the base of the trapezoid times the height of the trapezoid, and the sine is what made it the height. So then that's the area, or, well, I guess we said, yeah, that's what a cross product is. But I think thinking of a cross product as a way to find the area of a trapezoid when you have vectors is kind of dumb, because like there isn't a trapezoid there. If I have two vectors drawn, like why would I turn those into a trapezoid? I mean, there's no purpose in that. So the only reason I even mention it is just because it's at least a neat way to visualize it. But also there's an assignment question where they ask you for the volume of a parallel pipette. You probably never heard that term before, but a parallel pipette is like a 3D version of this shape. Kind of looks like this. So it's kind of like what a weird name for something, parallel pipette. It's kind of like a 3D trapezoid. So as a mathematician and as a person that just kind of thinks this stuff is beautiful, I kind of hate questions like this, just because what they're really saying here then is if you thought of this parallelogram that's in front of this as u and v, maybe I'll stick to the same orientation I had a second ago. If that's u and that's v, does it make sense if you had vector names for those two things? Then you could actually find this area that we were just describing right here. So you'd be able to find that area by just taking the cross product of vector u and vector v. And then if this distance was, say, 7, right here, then you could say times 7, and then you'd have the volume of that parallel pipette. But that's not an application. You see what I'm saying? I mean, that's what I've been calling in this class an application with quotes on it. That's just somebody saying, well, we just taught them this weird process of finding a cross product. And so, well, what are we going to use it for? That's a terrible example. I mean, your book, and most books are not going to talk about torque. I'm trying to help you understand this in light of a genuine application. So, and what it really is, what it's really from. But and there wasn't even pointing it out, I think it does maybe overall help your larger grasp of the issue. So let's look at just one other thing here, kind of pick up from something we did yesterday, and then we'll kind of take off and we'll take this to 3D. So let's figure out A cross B using two different letters this time than we've used before. Let's figure out A cross B in this context. So we'll say A, and this is going to be kind of like yesterday's example, because I want to keep everything nice and positive so that it works out beautiful. 2, 4, and we'll say B is 5. But again, I want to do this in kind of in the context of torque. And so let's just stare at this for a second, but I'm going to draw this in a little bit different way than I did yesterday. If I draw this as our X direction and this as our Y direction, I hope this is long enough. And we say, okay, vector A, this is going to be our distance, and this is going to be our force. I mean, that's really that's what this really means. Now, again, in the context of your assignment, they're just going to take the cross product and write the answer down. And, most people wouldn't even have any idea what they just accomplished. I just want you to know what you just accomplished. So if I go to the point, X is 2, Y is 4, right there. I see that our video is going to continue shutting off. That's nice. So there's our distance. And so what we're really finding here, I'm going to call this point O. What we're really finding here is the torque or moment around or about the origin or about the point O. And so there's the distance. And again, you're thinking of O as like the nut that you're trying to turn or something like that, or the center of the steering wheel that your type's trying to spin or something of that nature. And so there's vector A, but then we're going to take off and pull on that in the direction of 3, 5. So 3, 5 from that point there. Let's switch colors. So if I go 1, 2, 3 more, and then 1, 2, 3, 4, 5 more. Is that going to work out good? Doesn't seem like a very good choice. It's actually going to look better if we make this X bigger. Make the X 5 and this 3, something like that. I think that's actually going to look better. It was almost going parallel to the other one, if that makes sense, which didn't look quite as good. So let's see, if I went 5, 3 from there, I think that puts us right, at least reasonably right there. And so notice it's a little weird because I turned the axis kind of strange. So remember, this is positive X and positive Y. And so this is our distance, and then this is actually our force kind of pulling on it. And what we said yesterday is all we have to do is take the cross product of this. And notice it says A cross B. There's an order to that. So we said yesterday, if you take 2, 4 and 5, 3, and you multiply diagonally. 2 times 3 is 6, and then 4 times 5 is 20. Notice the order to that. And then you always subtract. You get negative 14. 2, 4, 5, 3. I'm going to erase this, but I wonder, would we get the same answer if we got this upside down? If I put 5, 3 on top and then 2, 4 on the bottom? Do I get the same answer for that? Notice you get 5 times 4 is 20 minus 2 times 3 is 6. You do get 14, but you don't get the right sign. So it actually does make a difference. Do you see that? So it's kind of the A vector. If it's A cross B, then the A vector is on top and the B vector is on the bottom. If you don't get that right, then you get the sign wrong. And in this case, what it means if you get the sign wrong is it's not rotating the correct direction. That's the problem. Like, what direction is it rotating? So that's just kind of interesting to point out, I think. Now, can you picture from looking at this? I know this is the part I want to add to today, in the sense that was nothing really new. But can you picture the fact that this, if it rotates, because all of this was happening in the XY plane, this is the axis around which everything is rotating. Can you picture that that's the case? I mean, that's what's going to be spinning. And based on the way the arrows are going, can you appreciate and agree that the spinning is happening in that direction? Do you agree that that's what's going to happen based on the picture that I drew?
Yeah, I can see that.
So
It wouldn't spin the other way?
yeah. So, I mean, if you, basically you'd have to be pulling in this direction to get it to spin the other way. Does that make sense? And so this is definitely spinning the way that I drew the green arrow around that axis right there. So my point is we got the number 14, but I just want to know, do you understand what that 14 means? If this distance was in feet and this force was in pounds, then that would be 14 foot-pounds. And then that's a a number that doesn't mean a lot to you, unless you got into the world of cars and tightening bolts, and because there is, like, you do have to tighten bolts in certain machinery in a certain way. It actually will say right on there, like if you're putting a bike together, that this needs to have 15 foot-pounds of torque, and there's a wrench called the torque wrench. When you pull on it, it actually has a little gauge that tells you what the foot-pounds actually is, and that's kind of cool. So these numbers mean something if you're in the world, in that business, so to speak, these units. But what's with the negative? Like, what does that negative actually mean? Now, based on the XY axis, notice it's curving from Y to X. In other words, if I had drawn it as we did yesterday normally, this is X and this is Y. The rotation is that way. And you would say, yeah, that's negative. Good, correct. Does that make sense? But the problem is we're about to do this in 3D. And so, like, what is positive and what is negative is really confusing. And I'm sure your book talks about this, although you didn't look, but there's this really cool trick called the right-hand rule. Have you heard of this before? You take your thumb.
Yeah.
Have you heard of this?
I just heard the name of it. I think I read it in the book.
Yeah, it's kind of cool. But this is how you determine positive and negative in the world of rotation. It's easy in the XY axis. You've already figured that one out. But see, if we jump to the third axis, then all of a sudden, this is weird. And right now, notice the axis of rotation literally is the Z axis. But this axis of rotation is about to be pointing in some totally random direction here in 10 minutes. It's going to be pointing some totally strange direction. And so it's like, how do we determine what's positive and negative? Remember, it's not so much a question of, did you get the answer right? Is it positive or negative? It's more as like, well, is that tightening the bolt or is it loosening it? I mean, it's important to understand what direction that's actually going. And so the right-hand rule is this: you take your thumb and you point it along the axis of rotation. And notice the arrow is pointing up here. So I point my thumb along that axis. And now these two fingers, this pointer finger is your x-axis, your, what is that finger? I want to say ring, but it's not. Your birdie finger, your middle finger. Pointer finger is X and middle finger is Y. Can you get your fingers in that position so that kind of matches the screen? Well, your fingers wrapping towards you is the positive direction. So you put this up and the way your fingers wrap, that's the positive direction. We'll notice this arrow is going the other direction. So we'll do this more. We'll do this a little bit more just so you get the hang of it. But thumb in the positive axis of rotation, and your other two fingers represent the other two axes. And if whichever direction they're spinning towards you, that's considered positive. Now, again, you need to understand there's nothing magic about positive and negative. That's a choice people make. We call sea level 0, and we decided anything up we're going to call positive and anything down we're going to call negative. Up feels like positive, down feels like negative. In the case of temperature, temperature goes up, feels like positive, down feels like negative. But that's very arbitrary. So it's more a question of, if I have an idea in my mind of how I think something's going to spin, can you get the same idea in your mind? I mean, that's kind of the idea. So stare at this picture right here. Given that this is going to rotate around this axis, can you put your thumb kind of towards you? And then based on the way your fingers are wrapping there, can you see that thing is going to be rotating against that negatively? Now, again, because you think of this as the y-axis and maybe this is the x-axis, and you already know that clockwise rotation is negative, you'd say, well, I didn't need that in this case. But as I said, we're about to go to 3D, and so we're going to need that now. It's not going to be as simple anymore as just clockwise is negative and counterclockwise is positive. So this force F, which has a magnitude, I guess we could figure that out, of 25 and 9, 34, a magnitude of the square root of 34. So that's like 6 pounds, if you will, of force, roughly. 6 pounds of force. And it's at a distance of, well, the square root of 2 squared plus 4 squared, the square root of 20. That's how much desire this would have to rotate. That's what a cross product is accomplishing. But again, when you get to your assignment, it's just going to say, take the cross product of this and write the answer down. And you'll find the assignment relatively easy, but you won't be able to apply this to anything. This is one of the reasons this class is a prerequisite to higher math. It's a prerequisite for engineering, for instance, is because of this kind of thing. So the question is, when you get there, will you kind of go, oh, okay, cool, I'm using this for something, or will you have totally forgotten it because of some irrelevant process where you multiply diagonals and subtract, and I don't know. Book said I was right. I don't know what I did. Okay. Let's take this 3D now. Apparently I didn't drag this thing in already. Now, I want to give you a shot at understanding what a cross product looks like in 3 dimensions. So this is going to show you what R cross F. Now, I like these 2 choices, and this picture that I stole actually came out of an engineering book, and that's why they picked vectors R and F, because R is the radius and F is the force. And I'm going to go back here and switch colors to help you see this a little bit better. So notice this is exactly the same picture I just drew for you a second ago, except that this R value right here, this radius is right here. There's your radius. Can you tell from the picture that to get from the tail at 0, 0, 0 to the head of it where the arrow is, can you tell that it's positive X, positive Y, positive Z? Let's stare at that a little bit. Notice to get to this point, you have to go positive X over to here, and then positive Y over to here, and then positive Z over to there. Notice R of Z is labeled right there, but that'd be the same length as this. R of Y is labeled over here, but that'd be the same length as this. So it's kind of like R is some vector, like I'm just gonna try to make it up. Like let's say R of X, let's say this distance is 3. Well, if that's true, then doesn't this look longer than that? Like maybe 5. And then how tall is Y? Well, that looks a little bit longer than this, so I'll say 4. Would you agree that's a reasonable picture as to where that vector is pointing? And all that just changed is I just added a Z component to it. That's it. Now again, I don't sit there, like interrupt, because I'd really like you to see this if you can. Because it turns out a cross product in 3 dimensions is a really crazy process. And I can teach you to memorize it. You don't have to memorize it. It's sitting on the note sheet that I gave you. So in one sense, you don't need to know anything I'm showing you to survive this class. But if you don't gain a conceptual understanding of it, like it isn't cool, it isn't anything fun, it isn't beautiful. And I also want to take you down the, down the rabbit hole of what engineers did, or, what mathematicians did to kind of create this thing. So do you see that there's like a box here? Just stare at the green box for a second and ignore everything else and just stare at that. And all that is just a box that kind of shows that the radius vector goes from the bottom corner at 0, 0 to the opposite diagonal corner in the room, if you will. But of course, that's hard to see in 3D, right? So there it goes up there. And so cool. Now we're going to say, okay, that's how long the wrench is that we're twisting on. And now we're going to back off and say, okay, well, how does the force work? Like, how are you pulling on this thing? And so let's take a look at what I haven't paid attention to now, which is this red force. So the red force is attached right to the end of that wrench. So the green R is the wrench. And now this is you grabbing and pulling on the wrench. And now you're pulling there. Notice there's like a brand new box there that describes what direction that goes. And notice, because this is a 3D drawing, you can't really tell where that goes. Well, unless you actually stare at that box a little bit. Can you see what direction that's pointing? If you stare at the box that they drew there. Notice it has an F of X, which is again going in the positive X direction. So it has a positive X. And then it has, according to this over here, a positive Y. So that's the force in Y. And then it has actually a positive Z as well. So basically the R vector was coming toward us and the F vector is coming toward us too. Do you see that? So the question is, what's this going to do? Now, again, I want to make some numbers up to that. Maybe we'll go draw this in, GeoGebra. So, and since these are forces, I'm going to make the numbers a lot larger. So let's see, but I'm just looking at relative sizes. Like X is pretty big. So I'm going to say that's, I don't know, 42 pounds. But then Y here, force of Y, that's smaller than that. So maybe that's 36 pounds. And then Z is taller than all of them. Z is longer proportionally than the other ones are. So I'm going to say that's 64 pounds. So these are all pounds, like the X in pounds, the Y in pounds, the Z in pounds. And for the radius, these are all feet, let's say. 3 feet, 5 feet, 4 feet. So the question is, how's that going to work? Like, that's going to cause rotation, right? But don't you find yourself staring at that going, I don't really understand where that rotation is now, because the axis that this is going to rotate around is not the z-axis now. It's like some axis that doesn't even exist. And then, of course, what's the numerical answer to this question? So the question here is torque. Now, let's see if we can visualize this. And whether you can visualize this will have to do with what I showed you yesterday, which if I didn't erase it, I'm going to show you again really quickly. This right here. The question is, can you picture what we did here, except in 3D? So let's just look at this picture again. So we had this vector, which was our radius, right? That was our radius. And then we had this vector pulling on it, exactly like we have now, except this was only in 2 dimensions. And so we said, okay, well, what's happening there? And what we noticed yesterday was that, well, I have this force here, V of X, but remember, this represents the axis right here. That's just kind of coming straight up toward us. What's its distance? So that's a force of some kind, V of X. Well, if I move it kind of over here, so Vx is sitting over here, isn't that its distance right there, which is U of Y? In other words, remember how they had to be perpendicular? So V of X times U of Y is causing rotation around in that direction. Do you agree with that, based on the fact that this arrow is pointing to the right? You cool with that? But then we looked at the other force, which I will now turn into pink. This other force here, but what's its distance? Well, if I move it down to here, isn't this its distance? Which was U of X. I mean, that's the U of X that's sitting right here. That's the U of X. So we have V of Y times U of X. But notice that's actually causing rotation in the opposite direction. Like those are fighting against each other. That's what we saw yesterday, right? That's what we did manually. Frankly, the easy way to get 20 and 6. But then we noticed, hey, they're fighting against each other. We can't add them. We can't add these. We got to subtract them. The question is, can you see this in 3D? And again, I'll post this so you can stare at this thing later and kind of try to get it yourself. But I would recommend, if you can either ask me a question or you can just say, hold on, like, give me a second. Let me stare at this for a second. Shut up. Like, that's totally fine. But I want to see if you can see the same thing happening in 3D. So let's see if we can go build this. So let's look at rotation in X. What's happening to get this thing to rotate around the X axis? So again, what am I looking at? I'm looking at forces, those red forces. Would you agree, this is kind of interesting, that the red force right here is perfectly parallel to this axis? In other words, it's pulling exactly the same direction, so it can't cause rotation around this x-axis. The F of X force is parallel to the x-axis, so it can't cause that kind of rotation. But let's take a look at this force right here, force of Y. Remember, force of Y was labeled over here. Then I can kind of draw it any place that I want to. But the question is, how far is that from, how far is F of X, how far is that from the x-axis? Well, if I move it over here, maybe you can see it. There's the force of Y. Isn't that how far it is from the x-axis? What is that length called right there?
Z.
What'd you say?
Z.
That's exactly right. It's the Z coordinate, isn't it? And there it is labeled right there. It's that distance right there. So this is the Z coordinate. So you have those two. So you have force F of Y times R of Z. And that is actually, because of the length of this arrow, that's actually causing rotation in this direction. Would you agree with that?
Yeah.
Can you see that?
Yeah, I could see that.
Cool. Now, stick your thumb around the Z, stick your thumb along the X axis. Is that rotation that I just got right there, is that positive or negative? If your thumb sticks toward the positive X, is that causing toward your finger rotation or the reverse of that?
I think it's negative.
It is negative. Do you see that? Say no, because I mean, we're going to see this a number of times. Say, I don't see it yet. Like, I don't, that's okay. That's actually negative. What about the Z force over here? There's the Z force, right? Isn't that F of Z? It's going straight up. Again, that's not where its label is written. Its label is written over here. That's the same vector, isn't it? Like, isn't that the opposite side of the box? So whatever, I mean, just pick this one. Let's look at this one. Fine, that's force of Z. How far is that from the x-axis? And again, it's got to be perpendicular. How far is force of Z from the x-axis?
Force of Y.
Maybe if I move it down here, you can see it. Isn't that force of Z? Isn't that perpendicular right there? Yeah, there it is. It's actually, its radius is Y. Do you agree that it's actually causing rotation in the opposite direction? Do you agree with that? So they're fighting against each other, just like it was in 2 dimensions. If you stick your thumb along the positive x-axis, aren't your fingers rotating in the positive direction? Can you see that this is actually a positive rotation, just like the other was a negative? So that's actually R of Y times F of Z. Those two things are causing rotation around X. Now, just for the sake of the numbers, isn't this exactly what we just saw a second ago? In other words, look up here. Isn't this R of Y, R of Z? This is F of Y, F of Z. So if I wrote 5, 4, 36, 64, or maybe I'll even just, since it looks a little more like what's down below, isn't that R of Y, R of Z, F of Y, F of Z? What did the cross product say? Didn't it say R of Y times F of Z minus R of 2 times F of Y? Like, isn't that what we just did a minute ago? Like, there's nothing new here, actually. Sort of mind altering to try to see it in 3 dimensions, but isn't that the same thing? Yeah, it is, actually. But notice it's kind of interesting that the X values had nothing to do with it. Like the force of X and the distance of X, it didn't weigh in there. Are you seeing why that's the case? Can you see that because force of X is parallel to X, it's not going to cause rotation around X? It's kind of pulling in the wrong direction. It's pulling parallel. Now it'll cause rotation around other axes, but it's not going to cause rotation around X. Okay, well, what about rotation? Is that color visible or is it weird looking? I can't tell. Can you see that okay?
It's okay.
Okay, but not great.
Yeah, it's okay, but not great.
That's fair. So now let's see what happens around Y. Now, just for a second, I'm gonna do Y, positive and negative. And I'm pointing my thumb toward Y. You hear that? This is toward the Y-axis, which means rotation toward me, because my fingers are positive, is positive, which means rotation in this direction, we say is positive. Whereas rotation in that direction, we say is negative, right? According to the right-hand rule. Isn't that interesting? It doesn't work with your left hand. It's got to be your right hand. So I point toward the Y. My pointer finger is up towards Z, and X is pointing right at me, my middle finger. So there's the axes. I've got that, and then it rotates toward me. And so, cool. So let's see if we can get the signs right for this one. So let's see. Well, we just had force of Z sitting right here, didn't we? Force of Z was sitting right here. That's going to cause rotation around Y. What's its distance? Isn't that its distance right there? Isn't that how far it is? Perpendicular.
That's radius X.
Yeah, isn't that radius X over there? And which one is that? Is that positive or negative rotation?
That's going to be negative.
It's going to be negative rotation. So you have R of X we'll take the color up to a little darker green. R of X times F of Z. And that's the negative one. What other force is going to cause rotation around Y? Well, based on the pattern, Y doesn't get involved, right? This is the Y-axis, so there's no Y. Well, we got force of Z, then there must be force of X by the pattern, right? So where's force of X? Force of X, force of X. Where the heck is that thing? There it is. How far is it from the Y-axis? Well, notice if I kind of copy this back, couldn't force of X be placed right there? If that's the case, isn't this its distance? How tall is that? What's that distance called?
R of Z.
Yeah, there it is over there. It's R of Z. It's that height. So this is R of Z. So it's, and what direction is that causing? Do you agree it's actually causing this positive rotation that we noted down there?
Yeah.
So it's R of Z times F of X. Do you see how that's also a determinant? That's another determinant. It's the same exact thing. So I can see a pattern emerging here. In other words, I see this is a Y, and then down here that means there's X's and Z's. And so I have a force of X and a force of Z, but the force of Z is not paired with the radius of Z. It's always like a mix, right? It's a force of Z and a radius of X, and a force of X and a radius of Z, right? It's not a force of X and a radius of X. So you see the pattern, like that happened over here too, right? There's X, no X's. I had a force of Y and a radius of Z, like the other letter. So can you already tell kind of without even looking at the picture then, based on the, I don't know, hints I'm giving you, if you will? Let's go brown and figure out the rotation in Z. Let's see, I'm thinking the rotain in Z. It's a new word, rotation in Z. I'm figuring that, well, Z is involved. So that means we must have like the force of X and the radius of Y and the force of Y and the radius of X. Do you agree with that? That's what it must be. But then it's like one's positive, one's negative. I don't really know. I mean, let's go ahead and go to the picture and like see it one more time. But that must be, if I'm catching on to this pattern, that must be what's going down here, right? So it feels kind of cool that this is happening. Okay, well, rotation around Z. Now again, you figure this out ahead of me this time. Put your thumb towards Z. What's positive rotation going to look like? Toward me. So isn't this positive rotation then? Fingers pointing, wrapping toward me. Now, again, this is the one axis you're actually familiar with. You've been living in the world of X and Y your whole life. You didn't know there was a third dimension. Isn't that what you always called positive? Look down at the flat plane of X and Y. Isn't that counterclockwise rotation right there? Like you've always been calling that positive. Do you see that? But we now have a system for making this work in 3 dimensions. So then going the other way must be negative. I think I just drew the same thing twice. There we go. So let's see if we can stare at this. And so now we've got the force in well, not Z, so X. We got this force in X right here. How far is that from Z? Where do I draw this? Well, I already drew it right here. How far is that? Well, we said it was R of Z away from the Y-axis, but how far is it from the Z-axis? It's that far. How far is that? Where's that labeled? Right there, R of Y.
R of Y.
You labeled it over here. It's R of Y. So is that causing negative or positive rotation? If it's right here and there's the distance. And again, I'm interested, can you see the 90-degree angle there? The force has to be perpendicular to the distance. Otherwise, this doesn't work. So isn't that this one?
Negative?
It's negative. So, you know, trying to write this according to the pattern, then I guess it's this one over here. So it's the radius of Y times the force of X. And so I'm kind of done now. That means I know the other one for sure. Then isn't the other one the radius of X and the force in Y by pattern? So can you see it? Can you find the force in Y and see that its distance is radius of X? It's already drawn there in the right position. There it is, sitting there at 90 degrees. Isn't it that far away? Force of Y is right there. It's that far away. Isn't that the radius of X? That's totally cool. So the problem in 3 dimensions, my friends, is that there's like, you can't just find one rotation. You got to find all of them separately. It's like X, Y, and Z are all separate. Notice right here that you just discovered, built exactly what we just wrote. So the letters are wonky, but to get rotation around I, which is, remember, code for X, it's basically the determinant of those, which would be UY times VZ minus UZ times VY. that was the rotation around X, wasn't it? Isn't that what we just did a second ago? Again, isn't it nicer with R for radius and F for force, so you can kind of see it doing something instead of just sticking numbers in there? Now, the reason mathematicians, and I want to show you something kind of cool now, the reason mathematicians spent some time with this is, where are we here? What's the date? What is today? No, that's not where we go. I guess we're doing this. Can you appreciate that this right here is going to be tough to remember? Because in 3D, there's a lot more diagonal multiplication going on. So this is the brilliance of the mnemonic device. So as weird as that looks, you can actually memorize this. Let me show you how. So if we said we would like to know what R cross F is, and R is actually a vector and F is a vector, and each of those is broken into its X, Y, Z components. 3, 4, 5, 42, 36, 64. It's broken into those three components. Then you write it like this, kind of a giant matrix. And the R values go here, 3, 3, 5, 4. They go on top. And then the F values go on the bottom. R cross F, not F cross R. 42, 36, 64. Now, that was all the numbers it took to create what we just did, right? But the fact that this was X and this was Y and this was Z is important to keep straight. So that's all you do is you write X, Y, Z. Well, the IJK version of that. So the question is, what do I do with all of this kind of diagonal multiplication business to just produce this up here without having to stare super close? You know, you can totally see you're going to mix this up. Even if you have this note in front of you, it's like R of Y, F of Z. It's like, I'm going to mix this up somewhere, but watch how this works. It's kind of nifty if you've never seen this before. All you have to do to get this to work, to get your I value, to get your X value, is cross out this, and then that leaves your little 2x2 determinant over there where you go 5 times 64 minus 4 times 36. Dunk, dunk. Now the question is, can you see that that's exactly, let's stare for a second at this. Can you see that's exactly what this formula said to do right here? What did this formula say to do? It says the Y value of R times the Z value of F. The Y value of R times the Z value of F, and then minus the Z value of R, 4, times the Y value of F, 36. Subtract those. Like that's memorizable. That's why somebody said, hey, cross product, let's invent something called the cross product. You're multiplying in the shape of a cross, and so we'll call it a cross product. You're multiplying in a cross. Hey, that's cool. We'll be able to memorize this. Like, don't think this is more than it is. It's a cool mnemonic device. That's all it is. Great. There's the I value. Now, how are we going to get, switch colors here, the J value? Well, in exactly the same way. Cross, cross. There's your matrix, 342, 5, 4. Or I'm sorry, 342, 4, 64. So I go 3 times 64 minus 4 times 42. And lastly, how do you get your Z component, which we're calling K? Same exact way. Cross this out, cross that out. There's your matrix. You go 3 times 36 minus 5 times 42. Boom. I mean, is that cool? Like you can actually memorize that. Now, unfortunately, there is one mistake in this. There's like a slightly deeper pattern to this. I want to see if you can catch this. This one right here is actually not right. Can anybody see that? There's a slight mistake in that one. This one does not match what this says up here. Can you see that?
It should be 4 times 42.
Yeah, see what this says up here? It says R of Z, the Z value of R. Remember for that middle one, we crossed this one out. So it says the Z value of R, which is 4, times the X value of F, which is 42. It should be 4 times 42 minus 3 times 64. Interestingly, that one's backwards. Like the pattern is kind of screwed up. Take a look at my note sheet that you didn't look carefully enough to see this yet before because I didn't give you enough time. But what do you notice about the Y component over here that I have expanded out? It's that right there. You can maintain the pattern that we saw, which is always multiplying diagonally in the same direction, because this is what's kind of a bummer. I mean, it's a bummer it didn't work, like I said, but remember, not we're creating this, we're discovering it. So it turns out the middle one is backwards. And by the way, there's a pattern for, you know, what's the determinant of a 4x4 matrix and a 5x5 matrix? This negative pattern sort of works its way through at a kind of a higher level of math. And if you're in 261, you either already know that or you will know that. So the best way to do this is just to leave it alone. Like, don't think, oh, that's right, I got to multiply backwards. Multiply backwards, just multiply forwards every time. But just remember that, oh, this one's a negative sign. That would actually switch it for you. Does that make sense? So this one's a positive, this one's a negative, this one's a positive. Now, those are just numbers, so I'm going to go ahead and write this out. Then your cross product, I'm going 5 times 64 minus 4 times 36, which is 176. So we get 176I, and then minus 3 times 64 minus 4 times 42. Would have been positive 24, but we have to make it negative 24. And then our K is 3 times 36 minus 5 times 42, which is already a negative number, so it will stay a negative number. So interestingly, the cross product in 3 dimensions does not produce a number. Remember in our notes a second ago, we got the cross product in 2 dimensions and it was negative 14. I want you to stare at that for just a second. We got negative 14 there. Would you agree though that that's actually negative 14? Well, K. Why do I say K? Can anybody tell me why I say K there? What does K tell us that was true, but we didn't really think about before?
Z-axis.
The
That's
Z-axis.
the Z-axis.
Yeah, isn't that rotation around the Z-axis? So if you throw the K in there, then you actually are adding the fact that, hey, this is rotating around the z-axis. That's not just negative 14 randomly in the universe. It's actually negative 14k. And in this case, that's all the rotation there is. It would actually be 0 rotation around the x-axis and 0 rotation around the y-axis. The entire thing is only rotating around the z-axis. What we're doing now is jumping to a dimension where you got to list all of the axes. And because our vectors were pointing in 3 dimensions, then we actually got answers for x, y, and z, not just for z. Does that make sense? Can't tell you how long this took me to kind of get my mind around, because both you can't listen to somebody once and understand it, but also I don't think people explain stuff simply enough sometimes. So you're getting the distillation of a lot of thought on my part to make sense of this. So the point is just, do you see how weird that answer looks? But it's no different than before. It's just that you have to separate it out. And there's an amount of rotation around x, an amount of rotation around y, an amount of rotation around z. Now I want to show you something really powerful and beautiful as a result of this. Let's see, this I think needs to go in the notes, which means I need to take a quick pick of our answers. So the only thing I'm regretting right now is I chose forces that were kind of large numbers. And so my R vector is going to be a teeny little vector, whereas my F vector is going to be gigantic, right? So you guys are mathematicians. Do you think I could get away with changing 42 to 4.2 and 36 to 3.6 and 64 to 6.4? And if I did that, would that just mean all these numbers are 17.6 and 2.4 and 10.2? Can I get away with that? I'm actually not sure. I'm thinking out loud with you right now.
Shouldn't it just scale down by the same thing if you
I
divide
think
them
so.
all?
Let's think about this over here for a second. So this right here would be 5 times 64, which was, 320, and now it'd be 3.2. No, I'm sorry, 32. So both of these would get 10 times smaller. I think this works, don't you? Because I'm afraid that's going to make the vector look really weird. So let's just try that, see what happens. We can always change it, right? So delete, delete, delete. So we had our R vector. Now I actually don't know. Can I label this thing R? If I label it R, is it going to screw it up? I'm going to try. It's lowercase, right? It seemed to like lowercase letters for vectors. And so let's see if it'll not get mad at us for doing that. So we said that was it 354? Near, 354. So 3, 5, 4. Sweet. It did not seem to mind that. We did consider that as a vector. Now this is cool, right? Because now we can draw a picture of what that graph that I showed you a second ago. So that's pointing toward us. Notice the positive axes are where the arrows are. So red is positive X, green is positive Y, blue is positive Z. So that's pointing toward us. I have this sitting just like that weird looking 3D box shape a second ago, but it's nice to spin it because now you can kind of see where it goes, right? It's a little easier to visualize. So that's kind of fun. Now let's throw the force on the end of this, right? Where's the force that goes on the end of this? Remember, that was a little harder because if I just draw in the force with those, 36s and 54s, 64s and stuff, that's going to start from 0, 0, 0, right? I don't want it to start from 0. I want it to start from that tip right there, right? So help me out. I'm trying to remember this. I think I had to graph the point. Please interrupt me if you remember different. We practiced this for a day. I have to graph the point 354. And because I used capital A, so now there's a point up there. But now I need the vector to take off from there, right? So it needs to go from A through the other point. I think this is how we did it. So the other point I'm going to call capital B. And basically from that point, we took off 36, 42, etc., right? So except for what we said is I'm going to try just saying 4.2, just to scale it down a little bit. 4.2 comma 3.6 comma 6.4.
I think there's also a way, if you just type in the vector, that you can click on the three dots, and then one of the options I think is to start at a certain point.
Let's see. So you're saying I could, and I'm not sure I'd be able to do this because I'm on an app on my phone as opposed to
yeah,
the larger
maybe.
version. But please repeat what you just said. You said you could just type.
Yeah, if you just type in your one as a vector, the 4.2, 3.6, 6.4, and you click on the three dots, I think there's like a setting that says you can start from a certain point, and you could type in that point in. So it's kind of,
yeah. And doesn't that make sense that they would do that? Because you see how tedious this is for us to do.
Oh, yeah.
So you might try what Ben said. I'm afraid to try it because I'm going to waste our time, and I have a feeling it might not work on this app. So I'm going to try that after class. So if I say I need a vector from A to B now again, did you notice a second ago that seemed to be pointing in a weird direction? Let's see. Oh no, that's actually not true. What I did here is actually not true. Do you see that that's not where this next arrow should go? The reason is it's got to go from A to there. Remember how this worked? I got the size of these things wrong. Do you understand why? Actually, I think I can even do something kind of cool down here. Let's just try this. C is equal to A plus B. That's what I should have typed. Do you understand that? I should not have typed B. So I'm going to turn B off. That's the point I should have been graphing. That's where this should be aiming, because that point started from 0, 0, 0. We're starting from the point 3, 5, 4, and we're moving 4.2, 3.6, and 6.4 from there. So now if I say vector V, I think I have to type the word vector here. I'm not sure about that actually, because vector is actually a command in here. And I'm hoping it lets me do this. So I need a vector from A to C. And notice it actually told us what that vector is. Sure enough, 4.2, 3.6, 6.4, right? So that's the picture we just drew. You agree with that? Except for I kind of made the fourth vector 10 times smaller. But they were both coming toward us. That's kind of the point. Now, here's where it gets interesting. The question is, what is that vector? What does the answer to this look like? So I'm going to type the answer to this, which I will call vector V. I can say vector V because I haven't used that letter before, and it likes that language. So if I say vector V is, and again, we got 176 for X, but I'm going to type 17.6. And we got 24, negative 24, but I'm of course going to type negative 2.4. And we got negative 102, but I'm going to type negative 10.2. Bam. Notice it's still pretty large. But what I'd like you to stare at is, where's that thing pointing? Does that make any sense to you? because the answer to this is a vector. That's the thing that's so weird. It's not a number. Can you, like, where is that thing pointing? Can you make any sense of that?
I don't think I can yet.
You might be able to see it if I stop right there. Do you see how the radius vector is pointing straight toward us? Right there. What do you notice about
90-degree angle.
90-degree angle? Do you see how it's 90 degrees to the way that thing is pointing? So that axis is actually set up perpendicular. It's actually perpendicular to the plane that goes through those original two vectors, just like this was. Let me, oops, I don't want to be here. In this original discussion today, the axis of rotation was perpendicular to the x, y plane. And isn't the xy plane where these two vectors live? Don't they live and actually create the xy plane? If I draw one vector, you actually don't know what plane it's in because there's all kinds of there's all kinds of planes that can pass through that. But if I draw a second one, does it make sense there's only one flat plane that could live in or that could land on that surface? And so this has to be perpendicular to the plane that's created by those two vectors. And that's exactly what we just saw in 3 dimensions. But we would, how do people learn this before they could cheat and visualize it like we just did? So in a sense, that's the significance of what we just calculated. What we literally got is the axis around all this, which is rotating. The other thing that's amazing is we got an answer here of -14, right? Let's see. That means that, let's see. That means that this length right here literally is -14. That's the length of that vector. Remember, the length actually means the force. The length of the vector means the force, or the miles per hour. Now, if it was negative, then that means that I actually go the other direction. Does that make sense? So what does that mean to us? So that vector there actually tells us the axis around which all this is rotating. But not only that, the length of that axis actually gives us the numerical answer to this problem. In other words, how much desire is there to rotate around that axis? So what's cool about answering this as a vector is you're not only going to know the answer to how many foot-pounds of torque this will cause, but you're also going to know what direction the axis of rotation is pointing. And you can appreciate if you're, in the space station, this would be a lot more important, right? Like, you fire a thruster in some part of it and it starts to rotate in space. Like, well, where? Like, how is it rotating? I have no way to make sense of this. And so if you don't have an axis around which something is rotating, you really can't talk about how it's rotating. Does that make sense?
So the
If I
actual
take
answer,
this pen and I throw it in the air, it's going to spin around, but the point is it's going to be spinning around an axis that isn't even there, but you could draw it in, and that's what we just did. Comment, question.
so the actual answer wouldn't be the magnitude of that vector.
Well, that's why vectors are so cool, because the best answer is to stop with what we have right here and say that's the answer, because contained in that answer is the axis around which it rotates. But then if we take the magnitude of that vector, then we can also know the numerical answer for how badly the space station is rotating. If we only report the magnitude, does it make sense that the axis is lost? But if we report the vector answer, which is what we have right now, then we can get the magnitude from it if we want. See the power in that?
Oh, I see.
Can't tell you how many hours I spent like trying to make sense of this stuff. Like, because I read what was in books, and books just said, do this and do this. And, I didn't understand, like, what is it? I just can't picture it. I can't get my mind around it. So
That's a lot of what 261 is.
oh yeah, great example. That is a great example. So hard to visualize all that stuff.
Yeah, and the first term of physics when they introduced vectors and the cross product and dot product, this definitely helped me a lot.
Yeah, I'm actually, any of you want to make comments about like places you've seen this before and things that were explained to you before that helped it make sense, or some of those kinds of things. But I know in my case, like as a student, I think I had to hear this kind of 3 different times, and even then I really didn't get it because of, again, some combination of I didn't think deeply enough, the teacher did a bad job, I don't know whose fault it was. In my case, I know myself well enough to know it was largely my fault, because I have to have things explained really simple in order to get them. But in my defense, I think that's true of all of us. I mean, getting the right answer, taking a cross product is very different than I understand what a cross product is and what it's accomplishing. Did that. Dang it, why isn't there another hour? I want to talk more about this. So actually, I think I better be putting this over here since that's where all this picture was. So let's just stare at this for a second and write a couple things down, and we'll see if we have time for maybe just at least one more simple example, because I spent all my time helping you understand this conceptually, which I do not apologize for. But I also want you to get your homework assignment right. Fortunately, your homework assignment in this section is really easy, and that was by design. So this is our R cross F vector, and it is perpendicular to the R and F plane. That's very important because we're going to use that perpendicular fact. This is a cool way to find a perpendicular vector. If you have 2 vectors and you take the cross product of them, and then you just found a vector perpendicular to those other vectors. That turns out to be a really cool application. But let's go one step further. So we're actually saying that R cross F, and hopefully this doesn't screw you up, that we're saying that R cross F is actually equal to the vector 176, -24, -102. That was actually the real size of it, despite the picture that I drew. And so if we said now, as the second fact, we would like to know the numerical or the scalar. So this is the vector answer, but we would like to know the scalar answer. And this whole scalar vector thing, man, that just hurt my brain. Like I just could not get my mind around that. And the scalar is a number, a vector is an X, Y, Z. And I just didn't understand how they spoke to each other very well. And I'm starting to get it now. I'm starting to make sense of that. If I take the square root of 176 squared plus 24 squared plus 102 squared, I get 204.8. This would be foot pounds. And if you think about units, isn't that what we did to get these numbers? Every single thing was a foot times pounds. So that's why the unit of this would be foot pounds. So basically, these 2 vectors over here are causing 205 foot-pounds of desire to rotate. But if that's all we have, then we've lost the axis. And here we have the axis built in. That's what's so cool about that as a vector. That axis is actually built in. And anytime I want to, I can go get the numerical scalar answer to this, which of course very important, right? It's like the space station. how badly is this wanting to rotate now because we just got hit by this meteor or whatever. I mean, you want to know 205, like that's an important number to know. But I also need to know the axis around which it's rotating. So that's a really powerful concept. Let's see if you can do this super quick, just as a form of practice. And we're late, so go if you need to go, because I'm not really going to teach you anything new here. But let's just try this really quick. So if I say U is 3I minus 2J plus 6K, so I'm giving you the vector in that form, and V is equal to 5I plus 4J minus 3K. And I ask you for generically, like we have no purpose in this, which is, again, most math books and all of your math assignment. What is the cross product of those two vectors? Notice the order. It's U cross V, not V cross U. Interestingly, while you're calculating that, Raymond sent me a cool extra credit yesterday that Joseph Lagrange is how you pronounce his last name. Looks like Lagrange, but Joseph Louis Lagrange in 1773 invented both cross and dot product at the same time. And he did it because he was studying one of the Platonic solids called a tetrahedron. But anyway, I won't elaborate on that. Which was cool. Thanks for sending that. I wish I knew more about that. It's really interesting.
Yeah, I thought that was really interesting too.
I was curious why he was studying that, because I wondered if it had to do with what I showed you guys today, which is, you can use this to find the volume of a 3D object. I was wondering if he was investigating that.
It must have been, yeah.
It's interesting. It's a shape that's created with 4 equilateral triangles. That's what it's hard to draw in 2D and make it look correct, but he was investigating that shape, which, by the way, turns out to be the shape of a lot of, a lot of chemical compositions, because they're all spaced evenly. Anyway, time to talk about that. So here's the way you typically set this up. I say I, J, K to keep track of which one is X, which one is Y, which one is Z. U is first. So of course, I could have made this tricky by writing it in that order, but then saying V cross U. I would never do that, but slow down and don't screw it up. So there's and what I'm doing is taking the determinant of this matrix, which is the I value times -3 times -2, which is 6, minus 4 times 6, which is 24. It's always minus. And then I got to remember this one's negative. The J is negative, but I'm crossing these two out. And I'm going 3 times -3, which is -9, minus 30. And then this will actually change the sign of it. And then it's plus K. And K would be these two. So 12 minus a -10. And so there's my answer. U cross V is actually equal to, you could write it any way you want. 6 minus 24 is -18. That'd be -39, but it actually gets changed to +39. And then 12 minus a -10 is 12 plus 10, which is 22. I think that's my answer. No application, no knowledge in a class like this that you're actually finding torque of something, but I'm getting the numerical answer. I mean, there's a whole bunch of questions in your assignment that just ask you to do that. It's like, I have no idea what I just did. The teacher just told me to multiply and divide and subtract in some idiotic order, which is how math feels to most people. So of course the question is, if I drew those two vectors, and notice those two vectors are no place in particular. And so again, we're over time, but this won't take me very long to do. I'm gonna graph these, except for I think I know what's gonna happen here, but I'm gonna graph these in GeoGebra without adjusting them. In other words, I'm not gonna draw them head to tail, I'm just gonna draw them. So U is this vector. U is 3, -2, 6. So that one would naturally, as the radius, be emanating from 0, but the other one isn't as natural. But it actually doesn't have to be drawn over off the point. It does in terms of kind of the torque application, but this isn't. We're just drawing it. So 5, 4, -3. Because remember, vectors can go anywhere. 5, 4, -3. So there's the two vectors. And so there they are in this kind of strange orientation. But now let's draw the answer in. And I think I can get away with calling the answer to this lowercase w. So we just kind of want to see, like, what did we just do? What did this accomplish? And we're going to make a bunch of use of this kind of starting next time. So that's why I want you to see this. So it was -18, 39, 22. My question is that correct? Is there something about that you can tell that's correct? What are you looking for?
90-degree angle.
You're looking for 90. And notice that other vector, the sort of the torque vector we just found is enormous. But notice if I line these up so that the U and V vector kind of aim in the same direction, so you can see the plane is flat now. Notice that really does seem to be taking off perpendicular. That's kind of cool, isn't it? So that makes me think I didn't blow it. That's kind of what I'm getting at.
Also, the rule of Saris works for the other 261 guys. Any other way of finding a determinant works for this.
What's your comment on that? Say that again.
The rule of Saris. It's just a way that we used in 261 to find the determinant a lot, and I've just memorized it.
Mm-hmm. So what we're going to pick up with the next couple of days is, this is a cool trick to find a perpendicular vector. I mean, if that's only your goal, it's like I'd like a vector perpendicular to that. There, you just found one. You know, maybe you don't care. Maybe you don't see whether there's a purpose for that, but I'm going to show you a purpose for that. But the meaning of this is you literally just found the torque. The length of that would be the torque. Well, if the U vector was the radius and the V vector was the force. That's just one application, but it's kind of a cool one. Anyway, I went too long. And I think you'll actually be okay with the assignment, just like this, but we can obviously pick up, what is today? Wednesday, Thursday, today's Thursday. I guess we're picking this up on Monday. Send me an email if you get stuck and I'll answer it. But I think we're okay. I'm gonna throw this in the notes and draw on it a little bit just so that it's there for you to stare at before I go. But feel free to stay after and ask questions.
Thanks, Doug.
Yeah.
Thank you for coming.
I actually had a question. Oh, go ahead.
No, go ahead. You're good.
So I've heard the word determinant come up quite a few times in this class, and I was just wondering if you could go over what that is, because I know in the quadratic formula, I think the determinant is that bit under the square root, I think.
Yeah, isn't that darn frustrating? Let's see,
Yeah,
is that the
so,
determinant? That's the discriminant.
oh, okay, I was close.
I will show you something cool about that, since you asked. About
It
what
was
the
it was like a magic number that we found in 261 that I didn't know what it meant until now.
yeah,
Okay.
like you found the determinant. Let me show you a place
Exactly, yeah.
where, yeah, and that's my problem is like, in a sense today we didn't get to enough applications, but you did leave knowing what a determinant will do, or what a determinant can accomplish, which I think is cool. And that's what I want to show you right now. Let's see, my screen went asleep again. So there's a way, there's a method called Kramer's rule for solving equations like this. If you have 3x plus 2 plus 2y plus 2y equals 12, and you also have 4x plus y equals 15 or something like that, and you're going to solve that. The process of solving that, one of the ways to do it is to say, well, I'm going to take this number and multiply it by this one. This is what you do in linear algebra. And then you say, I'm going to take this number and I'll multiply it up here by this one, so that I end up getting the same equation would be 12x plus 8y equals 48. And now this question one on the bottom is now 12x plus 3y equals 45. Why did I do that? Like, where am I going with this? Why did I do that? You guys tell me.
Well, you have a common factor of 12 now.
Yeah. So now they both have the same value, which if I then came and said, hey, I think I'll subtract these from each other, then 12x minus 12x would be gone. And then you'd have 8y minus 3y, which would be 5y. And then you'd have 48 minus 45, which is 3. And then you could say y is equal to 3/5, right? But stop and think about what you just did. If I wrote 3, 2, and 4, 1, which was the original matrix, if you will, here, didn't you effectively go 4 times 2 minus 3 times 1 to get 5? Now I just did that backwards because I sort of wrote it upside down, but that's why people invented a determinant, because it's just like that process right there comes up a lot. Like it came up with torque and it comes up here too. So if you said, my job is to solve 2 equations, 2 unknowns really fast, then you're really taking the determinant of this matrix. And if you think about this number 3 over here, wasn't it also a determinant? Because you really took 4 times 12. In other words, if you think of 312 and 415, which is these 4 terms, you went 4 times 12 minus 3 times 15. Isn't that how you got the 3? And so if you take this determinant here and you divide by that determinant there, then you get the answer. So it's like a really cool shortcut to like just get stuff done. And that's, so I've kind of harped on this a lot with you guys, but these mnemonic techniques are really cool. But the problem is if you teach these to people, then they get the answers, but they don't understand the answer they got. They're, like, what is this? I don't understand. You guys are in a spot to understand what I just showed you really quickly because you're good enough at algebra that I don't have to say that much about it. But if it's the first time I'm teaching you how to solve 2 equations, 2 unknowns, most people don't even understand that like those are lines that hit each other in the XY plane. And so what you're finding is the one XY point that works for both at the same time. And there's a lot of mental, time you got to spend visualizing this, which is why I spent all this time today drawing pictures in GeoGebra so you can kind of visualize what this is accomplishing. And so determinants are kind of cool. And that's why ultimately, Raymond, why they come up in 261 so much, because you're using them to solve linear equations. And that's why it's called linear algebra. And so I just showed you the two-dimensional version of a determinant to solve a 3x2 system of equations, if you will, or a 2x3 system of equations. But that ramps up to, 9 equations, 9 unknowns. It doesn't have to be 2 equations, 2 unknowns. So you just end up with these crazy determinants and multiple levels, and that's kind of what 261 really, grows out of. And that's why determinants are kind of cool. So they're a shortcut. They're a mnemonic device. There's nothing spectacular about them. It's just somebody recognizing that, hey, if I multiply numbers diagonally and subtract them, beautiful things happen.
Okay, yeah. Yeah, that's really neat. And that definitely clears up, kind of why I was wondering about that word that kept coming up. So
Yeah, it's kind of a neat.
Yeah, Kramer's rule, the way you did it, was a lot different than the way we did it, but it still does the same thing.
Yeah, I sort of did in my case, I'm doing it for Math 60 students. You guys are looking at it on a larger plane, on a larger, you're looking at it in 3 dimensions and 4 dimensions and 5 dimensions. So you're trying to look for a pattern that expands from there. But I showed you the conceptual underpinnings of where that thinking started, which
made sense, yeah.
Which is really cool to kind of see where that all kicks off. Because then if you say, okay, well, now let's try to use this to solve 3 equations, 3 unknowns, then all of a sudden the determinants are, well, they actually are what we just did today. They're like uglier looking determinants, and what you do with them, is challenging. And so, yeah, you end up taking, for Kramer's rule, you end up taking the determinant of one divided by the determinant of the other, and that'll produce the X. And then the determinant of a different matrix divided by the determinant of another matrix gives you the Y. And
Yep.
And for Z, and then you can go to 4 equations, 4 knowns, and the same answer. And it's really, I don't know. To me, this is absolutely zero fun as a student or a teacher. It's negative fun if I can't see what this is accomplishing, if I can't see what this is doing for me, And my experience of a student, like most, is that the teacher explains something and it now makes sense to them, either because they were just really smart to start with, or because they've taught it 10 times. And so they see it, man. And, you can tell I do. You can tell I'm explaining this and totally seeing it. But if what I'm showing you, is for the first time, it's pretty tough to take that in for an hour and a half and actually see it all. But I think the illustrations go a long way toward making that make more sense.
yeah, they definitely do. Okay. Have a good weekend, Doug.
You as well.
All right, I'm out. See ya.
See you guys.